In the last class, we started with a set of points. We deliberately took x-axis for the abscissa value, the x-axis values in discrete interval, and those are the correct values. And y-axis value, we took it as a noisy one, and we tried to fit one line so that the line represents the best possible way the data points. So that is what I wrote here. X values are correct, Y values are noisy, and these are the set of data points. And the line equation, you know, Y equal to mx plus c. And these are the set of linear equations that can arise. Y1 equal to mx1 plus c, and so on, yn equal to mxn plus c. So the number of variables that are unknown here is m and c. What you know is y1 to yn, x1 to xn. So if I put this entire set of linear equations in the form of a matrix, this actually becomes all these y1s uh, okay, small gauge. Uh, yeah, if we put all these equations, all this entire set of equation y1 to yn in the form of a matrix, so then it actually becomes on the left hand side, it becomes a one n cross 1 matrix comprising all the y's, and on the right hand side it becomes multiplication of two matrices. One matrix is the unknowns m and c. The other matrix is again n cross 2. So n number of rows, that signifies the set of equations, and two columns. So these two columns matches with this matrix MC. So now here we came, now we have a bigger problem. Well, this represents our famous equation Ax equal to B, but then we are in a bigger problem now. The bigger problem is that the number of variables are way less than the number of equations we have. And this is what we call, it's an inconsistent, the solutions would be inconsistent, the system of equations are overdetermined. These are overdetermined. So what do you mean by overdetermined? That in order to have a consistent solution, M and C, that is the, um, in order to have a consistent solutions for this M and C, what we need is B has to be in the column space of A. If B is not in the column space of A, you do not get a consistent solution. Now, in order to solve this, we started with the least square things. We started with the least square things. Uh, okay, so if we consider all those points, let us take some sample points like x equal to b1, 3x equal to b2, like that. I've taken some sample points, and what is the best thing that we can do is the line that passes through all these points, or the line that represents all these points, should have minimum error. That is, x minus b1 should be as close to 0. So similarly, 3x minus b2 and so on. So the sum of the squared errors should be as low as possible. And this is what we started with. In order to, if we can solve this particular equation, like we know analytically, that uh, the first derivative of this equation at the would be equal to 0 whenever you want to find some minimum value of this, and that is what we explored here and found out what is x. We found out what is x. Now when we found out what is x, this came out to be this particular equation, and finally x cap. Like why I wrote x cap here, because it is a best estimate of x. It is not the exact x, rather it is the best estimate of x. So I wrote x cap. X cap is equal to A transpose B upon A transpose A. Now this has the resemblance with what we saw in our previous class, that is the projection of B onto A. That is what we found out here. And in this regard, if I go back to that, the projection of B onto A projection of B onto A, this is what the error term, here I have written C is equal to B minus P, and this is what exactly we have done there. So whenever there is an error term, that this perpendicular distance, this error term has to be minimized. That is what the whole concept is about. Now we did this one for a single variable. Now if there is a requirement for multiple variables, can we do it using a matrix, a set of, instead of having a set of linear equations, how in an elegant way we can do that? That is what the next concept is about. And we started with this one, B is equal to AX, and this is from where I would like to continue. AX equal to B. Now this part, AX equal to B, this is where we started. I mean, this is what we talked in the last class. Let me start from that point itself. So we have Ax equal to B, which is overdetermined. X equal to B, which is overdetermined. Now, if we look at the diagram, what is that? Uh, we have A, we have B. Now we have a projection, isn't it? This is what is P is, and this is what the error term is. And in vector notation, P plus E is equal to B, or E is equal to B minus P. That is what we did on that day, that previous diagram that I showed you. So uh, okay. So what exactly I can write here is B is equal to this P plus the error term, which I can write it as P plus B minus P. The same thing I am writing. B is equal to P cancelled. That is what the thing is. Now, what exactly this B minus P, this error term is? What exactly it is? This is 90. isn't it? Or so to say, this part is orthogonal to the column space of A. This part, if I say it is orthogonal to the column space of A, this is also orthogonal to the row space of A transpose. Now, in one of our previous class, we saw what is the relationship between row space and null space. What is the relationship between row space and null space?
They are perpendicular to it.
Yeah, they are perpendicular. If you just go back to the previous class notes, I hope you can see, right? Uh, when I drag up and down or something like that. Null space. Null space contains solution x to ax equal to 0. So null space contains solution x to ax equal to 0, and that is what the column space of A transpose or the row space is perpendicular to the null space. That's right. So that is what we can write here. We can utilize that the same thing. And if this is this error vector b minus p, if this is orthogonal to the row space of A transpose, that means this particular vector is in the null space of A transpose. Okay. Now, if it is in the null space of A transpose, what the best thing I can do is if I perform a dot product with A transpose, then this term would vanish. Okay. So that is what I can start writing here. AX equal to B. Let me pre-multiply it with A transpose. Why? Why should I pre-multiply? Because I want to get rid of this error term. Okay. Now this gives rise to one of the wonderful equation in linear algebra. It's called normal equation. Normal equation. So let us explore this one further. So what I can write here from this normal equation I can get is x is equal to A transpose A inverse A transpose B, or if I again multiply with AX, which actually I want from here, AX equal to A times A transpose A inverse A transpose B. And this is nothing but B. and this B is nothing but here the projection P. Okay, so this I can call it as a projection matrix. If you recall, X cap equal to P times B and all those we saw in one of the previous class. I mean, everything will be correlated now. Now, this is this all we started with like um, A transpose uh, this B minus P, B minus P is AX. So like that, A transpose B minus P is equal to 0, and then that way this everything started. But then there can be another interpretation of this. There can be another interpretation. Let us look at that interpretation also. Well, I have a column vector A. Oh, I'm sorry. I have, yeah, in that previous diagram, what did I say? Like here you have one vector A, one vector B. Now we have, instead of having one vector A, let us have a column spans, multiple vectors we have. So in that case, how this goes? Let us say we have one vector A, one column A1, another column A2, okay? Like that, different columns are there. And this creates a span. And we have a vector B. Vector B, this B will be projected onto this column span A1, A2, A3. Let me say this is what the projection is, because this is what the vector P would be. What I need here, again, a representative vector like P from which upon which I can project B and so on. So if you see the error vector, or if you see this error vector must be perpendicular to each of these column vector A1, A2, A3. That was for single variable. For multiple variables, if I see multiple number of columns, if I see this error vector, it should not be just perpendicular to one of the vectors, rather it should be perpendicular to each of those columns A1, A2, A3. Okay, so in that way, if I write A1 transpose B minus AX cap, this is equal to 0. And similarly, AN transpose B minus AX cap, that is equal to 0. Or in the form of matrix, if I write, this becomes A1 transpose, A2 transpose, AN transpose. So these are the transpose values are there. So this multiplied by one column, that is B minus AX cap. Sometimes this doesn't respond properly. This is equal to 0. Now, what exactly is this? This is again the same thing. A transpose times B minus AX equal to 0. What is the same thing? It is the same thing, in fact. A transpose B minus AX equal to 0. Or so to say, A transpose AX cap is equal to A transpose B. Now, if you calculate the errors and all those, this would result in the same thing what we have seen earlier, and the same normal equations only you will get. Okay. Now, for the sake of, completing with one of the, illustrating this one as how does it work. Let us see one example. Let me have a system of equations like mm, let us say we had y equal to mx plus c. That's right, mx plus c. So this m and c, let me have values. Sorry, this x and y, let me have values like 1, 1, and 2, 3, 3, 2, like that. I have three values, x and y. Okay, so let me put this one in terms of an equation. In terms of a matrix, the matrix that we saw in the last class, this particular matrix, this matrix. Okay, y1, y2, yn, x1, 1, x2, 1, m and c in that way. Okay. One, two, three, that is y is equal to uh, 1, 3, 2, 1, 1, 1. Okay, so this is what we have, a x equal to b. That's right. So the formula that we have is A transpose A x is equal to A transpose B. A transpose A x is equal to A transpose B. So A transpose is I mean, this A transpose becomes, row becomes column, 1, 1. This is A transpose, right? A transpose A. This is what I'm writing actually. A transpose A X is equal to A transpose B. Normal equation. This format I am writing. So let us multiply these two. How much this becomes? 132 times 132, that becomes 1 plus 9 plus 4, 14. 132 times 111, so that becomes in the Pajik Cho. This also becomes 6 and this becomes 3. MC, and this becomes 4. No, Cho, 13. Object Cho. Okay. So what is this actually is a linear system of equations, like you can easily find out what is the MC, but then let us go by what we have seen. Our method X is equal to A, A transpose A inverse A transpose B. In that way, let us see, that is X cap is equal to A transpose A inverse A transpose B. In that way, let us see. So here actually I need to find out the inverse of this particular matrix, and it's a 2 cross 2 matrix, quite simple. Like MC becomes, its inverse becomes actually um, what you do with inverse, you swap this one, 3 14 minus 6 minus 6. So this actually becomes 39 minus 6, that is 3. 6. 6, right? 13 6 ja 78, 14 6 ja 84. 84 minus 78 is equal to 6. This I can always write as 3 6, or if I take 3 common, this actually becomes 1 2, or if I take 6 out, that becomes half 1 or 1 2 also I can write.
So while calculating inverse, we also have to divide it with its magnitude, right?
Yeah, but then that common part, that is I'm not taking into consideration, like the way I have taken 3 common here, it's the same vector, right? M and C, the same
Okay, sir.
values, scaled version. That is why I just ignored that. Okay. I'll take another example from the book actually that is much more realistic. That particular example is, you try to correlate, try to understand what exactly the things are from one of the book I'm taking. Let us say A is equal to 110, 230, and B is equal to 456. Now look at this, the first column. First column, Z value is 0. The third dimension is 0. Second column, the third dimension is also 0. What does it mean? They are in the XY plane. The Z value is 0. But here, the Z value is 6. And this is somewhere the problem comes. Overdetermined solutions like that. Okay. Now, um, so the column space of this A, these two column vectors, they lie in the XY plane. And this B vector, it is something like this here. Let us say this is X, this is Y, and this is Z. So I have one vector 1 1 0. So let us say this is 1 1 0, and another vector 2 3 0, 2 here, 3 here, let us say here. Okay. And this is the column vector. This is A1, let us say. This is A2, let us say. Okay. So this is A1, this is A2, and I have a vector B 4 5 6. So somewhere here, B 4 5 6. Let me not take that big. B 4 5 6. So the projection of this particular vector will also be in the XY plane. Oh, sorry, not the opposite. The projection will also be on the XY plane. So what the projection would be? Obviously the projection would be 450. By seeing it we can say, but then let us find out how it becomes. So X cap is equal to A transpose A inverse A transpose B. So A transpose uh, A transpose. What is A transpose? 1 1 0 2 3 0 1 2 1 3 0 0. I have, let us say, x1 cap x2 cap is equal to A transpose 1 1 0 2 3 0 4 5 6. Correct? So this becomes 1 1 0 times 1 1 0. This becomes how much? 2. 2. This 2 when multiply 5. This 2 and multiply again 5. And this one is a bigger number. 2 into 2 4. 3 into 3 9. 13. Last one is 0. So x1 cap x2 cap. This one becomes 9. 4 plus 5 9, right? Yeah. 8 plus 3 15 23. Fine. So x1 cap x2 cap. This becomes 13 2 minus 5 minus 5. Just try to find out how much this is. Thirteen into 9 117 minus 23 into 5 2. That's a small number. So again
So 2
945
comma 2 by 1. So 2 and 1.
45. So that is what 2 and 1 we are getting. Yeah. Now 4 5 6. That is what I told you actually. When this B vector is projected onto the xy plane, B vector when projected onto the xy plane, 4 5 6 is the vector. When it is projected onto the xy plane, so this becomes 4 5. So the projection would be 4 5. Now we have x1 x2 h2 1. Now there is another component 6. That is what is our error actually, isn't it? So if we see um, this value, yeah, this value, This is where the entire thing is. 0, 0, ax equal to b, right? That is what we write. Ax equal to b. X is 2, 1. A is 0, 0. And this is what the error is. 6. So this is something like 0 times 2 plus 0 times 1 is equal to 6. This is what is your error. Okay. Okay, then we'll stop here. We'll see a couple of few more things in the next class. And okay, thank you.
Thank you, sir.
Thank you, sir.